First, why fine-tune at all? A base model is a generalist. It knows a bit about everything, but it doesn't excel at your specific task. Maybe you want it to sound like your brand voice, or answer technical questions in your domain, or follow a specific output format. Fine-tuning adapts the model to exactly what you need. The old way was full fine-tuning, updating every single parameter in the model. A 7 billion parameter model at 16-bit precision uses about 14 gigs for its weights. But during training, you also need optimizer states, gradients, and activations. That stuff pushes memory usage past 40 gigabytes for a relatively small 7B model. So if you had an RTX 4090 with 24 gigs, you were locked out. That's why nobody fine-tuned at home. Until parameter-efficient methods came along. In 2021, Microsoft published a paper called LoRA, Low-Rank Adaptation. And it flipped the whole problem on its head. The idea is brutally simple. Instead of updating all 7 billion weights, you freeze the base model. Then you inject two tiny matrices, call them A and B, into each attention layer of the transformer. These matrices are low rank. They have way fewer parameters than the original weights. Instead of training 7 billion numbers, you train maybe 500,000. On GPT-3, which has 175 billion parameters, LoRA cut the trainable count down to just 37 million. That's a 10,000 to 1 reduction. And here's the beautiful part. After training, you can merge those tiny adapters back into the base model. Zero inference latency. It's like the LoRA layers just dissolve into the original network. No performance hit at runtime. The default rank, that's the R value, is 16. That's the sweet spot for consumer hardware. Enough capacity to learn the task, not so much that you waste VRAM. LoRA was a huge leap. But it still required the full base model in 16-bit precision. A 13B model needed 26 gigs just to load, that's already over budget for most consumer cards. Enter QLoRA. Published in 2023 by Tim Detmers and team. The insight: quantize the base model to 4-bit first, then apply LoRA on top. The base model loads in a special 4-bit format called NF4 normal float. It's information theoretically optimal for normally distributed weights. Gradients backpropagate through the quantized base into the LoRA adapters, which stay in 16-bit precision. Then they added double quantization, quantizing the quantization constants themselves, and paged optimizers that use CPU memory when GPU memory spikes. The result? A 65 billion parameter model fine-tuned on a single 48 GB GPU. That's 780 gigs down to 33. The resulting model, Guanaco 65B, scored 99.3% of ChatGPT's performance on the Vicuna benchmark. The quality loss was essentially zero. Let's get practical. Here's what fits on real hardware you might actually own. On an 8 GB card RTX 4060, RTX 3070, you can fine-tune models up to about 4 billion parameters with QLoRA. Think Llama 3.21b, Phi 3 Mini, Qwen 3 0.6b. Batch sizes of 1 or 2. Tight, but it works. Use Unsloth's optimizations. 12 gigs RTX 4070, RTX 3060 12 GB opens up 7 billion parameter models. Mistral 7B runs fine with QLoRA. Small batch sizes, but you're training real models. 16 gigs RTX 4080, RTX 5070, here it gets comfortable. You can run Llama 3.18b with solid batch sizes of 4 to 8. And 24 gigs RTX 3090, 4090, 5090, this is the sweet spot. You can push up to 34 billion parameters with QLoRA. Do full LoRA on 8B models. Run batch sizes of 16. Train 10,000 examples in 2 to 4 hours. That's when consumer fine-tuning becomes a real workflow. So you know the theory. But what tool do you actually use? For most people, the answer is Unsloth. Unsloth is an open-source framework that replaces HuggingFace standard trainers with custom Triton kernels, GPU code written to be brutally memory efficient. Their claim: 2x faster training and 70% less VRAM than stock QLoRA. with zero accuracy loss. How? Custom kernels for rope, MLP, attention, all padding free and fused together. They support over 500 models. Llama 3, Qwen 3, Gemma 4, DeepSeek, even mixture of experts models. For Mo models, they claim up to 12x speedup. And if you don't want to write code, Unsloth Studio gives you a web UI. Upload a PDF or CSV, it builds a dataset, then you click train. There's also dynamic GGUF export, train your adapters, then export straight to llama.cpp format for inference. Installation is one command, curl Unsloth's install script. That's it. If Unsloth is the fast, easy path, Axolotl is the production-grade alternative. It's YAML-driven. One config file defines your model, your dataset, your hyperparameters, your quantization method, and your evaluation. Axolotl supports more training methods than any other framework: full fine-tune, LoRA, QLoRA, DPO, GRPO, ORPO, even quantization-aware training. It handles multi-GPU setups with FSDP, DeepSpeed, and Ray. It scales from a single card to a cluster. The trade-off: it's more complex. You need to write that YAML config by hand. But when you need reproducible, trackable experiments, or when your team needs to share training configs, Axolotl is the right choice. Both Unsloth and Axolotl build on the same foundation: HuggingFace Transformers Reinforcement Learning Library, TRL. TRL's SFT trainer is the standard workhorse for supervised fine-tuning. It handles chat templates automatically, packs multiple examples into one sequence for efficiency, and lets you train only on the assistant's responses, not the user's prompt. The integration is seamless. Add a peft_config parameter with your LoRA settings, and you're running QLoRA. Change one class to DPO trainer, you're doing preference alignment. GRPO trainer for reasoning style RL like DeepSeek or one. You'd go direct to TRL when you want maximum control. Unsloth and Axolotl add convenience. But TRL is the engine under the hood. Here's the single biggest factor that separates a good fine-tuning result from a bad one, and it's not the tool. It's your data. You don't need a million examples. With LoRA, 1,000 to 10,000 quality examples is usually enough. And quality is far more important than quantity. 1,000 hand-curated examples will outperform 100,000 web-scraped ones every time. Deduplication is critical. Duplicate examples cause the model to overfit and hallucinate. You also need format consistency, every example should follow the same template. And the chat template must match your model exactly. Qwen uses im_start, Llama 3 uses header IDs with special tokens, Mistral uses square brackets around instructions. Get this wrong and your model won't know how to talk. One more thing, assistant-only loss. Only train on the assistant's responses, not the user's prompt. This prevents the model from learning to parrot the instruction back at you. Let's talk numbers that work. These are the hyperparameters that make or break a fine-tuning run. Learning rate, start at 2 × 10 to the power of -4 for LoRA and QLoRA. That's higher than full fine-tune, because only the adapter parameters are training, you can push harder. For full fine-tune, drop to 2 × 10 to the power of -5. Batch size, push it as high as your VRAM allows. 1 or 2 on 8 GB cards, up to 16 on 24 GB. Then use gradient accumulation to reach an effective batch size of 16 to 128. Sequence length, stick with 4096 tokens. That's the standard. Longer sequences eat VRAM fast. With Unsloth's packing, multiple examples can share one sequence. LoRA rank, R=16 is your default. Drop to 8 for quick experiments or tiny datasets. Go to 32 for harder tasks or bigger data. And epochs, for a dataset of 1 to 10,000 examples, 2 to 3 epochs is enough. Monitor the eval loss. When it plateaus, stop training. More epochs doesn't mean better results, it means overfitting. Okay, let's address the elephant. Is QLoRA as good as full fine-tuning? For most consumer use cases, yes. Instruction tuning, style adaptation, format following QLoRA is indistinguishable from full fine-tune in practice. The Guanaco results prove that. But there are limits. For heavy reasoning, injecting new factual knowledge, or massive domain shifts, full fine-tuning still wins. LoRA has limited expressivity, about 0.1% of the full parameter count at rank 16. You can't learn entirely new domains with that. What about catastrophic forgetting? With LoRA, it's actually low. The frozen base model retains its general knowledge. The biggest risks are safety alignment. Your fine-tuned model might lose guardrails and factual accuracy if your training data is bad. Current consensus: for 90% of consumer fine-tuning, LoRA and QLoRA are all you need. The remaining 10% is where you'd want data center hardware and full fine-tune. And that's fine. If you're running local LLMs, fine-tuning is the next step, and you probably already have the hardware for it. Subscribe for more deep dives on practical AI. And drop a comment: what's the smallest GPU you fine-tuned on? I want to hear the war stories.